Thanks, Robert, for the nice review of March. I'm going to step back a little more than just 1 month for this. By the way, this is a set of slides that sort of does not capture what I think about the whole project. This is sort of like a history, and this has been carried together by a lot of people, actually very notably Costas. And yeah, let me ask you before I start, who actually has known this Omnius Stratosphere project that came before Flink? Okay, but also quite a few have not known it, right? So, yeah, to go back, actually, we don't have to go back all that far because the project is sort of new. If we go back just a little bit, if you look at the date, it's less than a year ago. We were very happy to make this announcement. Stratosphere accepted as an Apache incubator project. So at that point, I think we were all still, or the people that are now, let's say in data artisans in the company, were still at the University TU Berlin. We were working on our cool project Stratosphere and so on. We're hoping to get people excited, and some of the people got excited enough to just tell us, okay, you know what, please bring this to Apache. This is a very nice project, make a proposal, and the Apache incubator actually voted this project in, and it finally became an Apache project. And what did it look like back then? Robert just gave you a lot of nice announcement. What happened just in March? So a lot has happened since then. If we look at the state of the system when it entered the Apache incubator, it was basically this. It was some weird thing called the packed API. Some optimizer and a packed runtime and Nephilim. So really, really weird names. Probably the people who still know it from the Stratosphere times will figure out what it is. It has some. It sort of relates to the different groups that worked on different packages in the system. It was a, let's say, not so very nice to use API in Java. It was an unstable optimizer, and it was a runtime that did some neat things, but could use a lot of usability work. Yeah, that was Stratosphere version 0.2. We then started actually when we got this announcement. You know what? It's going to be Apache, and we got all very excited. So we got very, very busy and added a few things. We added a version of the API in Scala that followed a very different paradigm. It followed this paradigm of writing programs centered around data sets, which now is also the variant that the Java API uses. But we first prototyped this for the Scala API, and we also added, just for usability for people, a few different ways of executing it locally, remote, and I think Robert hacked together the first version of Yarn, which sort of worked. So that was Stratosphere 0.4, and we were so excited about these many changes that we actually skipped a version from 0.2 to 0.4 just to tell everybody, you know, we did so much. But things actually, I think they accelerated a little bit after that. So version 0.5, even though it looks like there is like a marginal change from 0.4 to 0.5, it's just this little box dataset API in Java. I think this was like a major thing, because this is like the basic bricks for the API that we're basically now giving to people for batch processing, and it is very different from the previous API. So everybody who has worked with this packed API before and then switched to this, it's like really day and night difference. And it came with a lot of tooling around it, actually, with distributed cache, with stable support for iterations, with ability to, you know, not just plug in distributed sources, but also just connect it to Java collections, JDBC data sources, H-based data sources, Hadoop data sources, interoperability with Avro, so all the stuff that people actually need when they want to use it. So the change from here to there was actually pretty big, even though it only reflected in one box. And then the next thing was, actually this whole thing was I think 2 months into Apache, and we did our first official Apache release. So it was then called Flink. We had a bit of a struggle to find a suitable name. When we entered Apache, it was still called Stratosphere, but it was pretty soon very clear that we cannot keep that name for various reasons, name conflicts, and also legalities had to do something with it. So from 0.5 to 0.6, one big part was just to move everything to the Apache infrastructure, but also there was more behind it than it looks, because in the runtime, which is now the Flink runtime, we did a lot of improvement on the network stack. So people who had previously tried out Stratosphere before and then moved to Flink will probably have noticed the difference, that some jobs just worked that did not work before. From Flink 0.6 to 0.7 is a pretty big change in the picture again. This is when we first started adding support for streaming programs. So the stack before is just batch processing Java and Scala, working sort of different, and then the optimize and runtime. And we started building the entire streaming stack next to it. So data stream API in Java, sitting on top of the stream builder. The data set API between Java and Scala is now actually unified, so they're like almost exactly mirrored, with some minor syntactic sugar for the languages. In the Java and Scala API, full support for POJOs and by name addressing, MapReduce compatibility. Another backend here for executing Flink programs not in the cluster but embedded in other Java applications. Full MapReduce compatibility, more scalable ways of distributing libraries, more support for different file systems and all that. 0.8 added actually a Scala API for streaming. So now on the streaming side, we also have Java and Scala APIs, which are sort of mirrored, and the Scala and Java APIs in the data stream, in the data set, basically follow almost the same kind of paradigm. So the switch from a streaming to a batch program is extremely lightweight. A lot of performance enhancements, serializability integration with Cryo, extended support for different file systems, Windows support in the streaming API, and so on. And 09 again, 09 is a very big change again, mostly visible actually in the amount of libraries that exist on top of the system. So aside from a completely new distributed runtime that a few people have sort of spent their entire time working on with distributed coordination based on akka, a completely new network stack that is actually now a hybrid stack between batch and streaming, a different or an additional execution backend in Tez. We now have on top a API in Python, not yet fully merged, but a sort of final pull request, a graph API called Jelly for computation on graph data structures. It gives you just an object called a graph that encapsulates data sets that represent vertices and edges, and you can run algorithms on top of them, typical graph algorithms, page rank, connectivity, communities, and it also gives you templates to implement your own graph algorithms in various paradigms like vertex-centric computing, gather, apply, scatter. The table API that Robert just showed is also in there. It's like a precursor to SQL. SQL basically in a Java-ish or Scala-ish style, like language integrated queries, the Link tool that you may know if you work with Microsoft SQL Server. A machine learning library, the sort of almost newest edition, but one of the most active parts right now, where I think new algorithms are coming in like almost on a weekly basis. The gray boxes here are things that do not belong to the Flink repository, but work together with Flink. So Dataflow runner on top of the batch API, Dataflow runner on top of the streaming API is still in the works. Samoa is a project that is machine learning on data streams. So not machine learning on a data set that is at rest, but a data stream as it comes. You train a model, you feed back part of the model into the stream, and so on, and keep on evolving the model on the fly as it comes. It's another Apache project that now has I think also a pending pull request as a runner for Flink. Yeah, so that is, if we do the speed run from here, there. It looks like a few releases. It is less than a year, like something like, I think, 10 serious months spent on this. And yeah, what came out of it is, I think, almost a complete rewrite of the system, which is quite a bit because the system is a few 100,000 lines of code by now. And from a system that does some batch programs, I think it is a pretty impressive diversification that this community has made there by adding real-time streaming, adding front ends for for various paradigms, for linear algebra and machine learning, graphs, for logical languages like in the table API, streaming API with Windows, batch API with datasets and so on. A lot of different backends, which is actually something that you don't notice so soon if you first check out the project, why this is actually extremely valuable. But they all come in very handy in different environments, like debugging, running it on a standalone cluster, running it on a shared cluster, running it on an elastic cluster, running it inside a web container. You write the one program and you can run it in almost any environment that does have to do something with crunching some data, computing something out of some data points. That is the whole point of adding these different backgrounds. Make Flink run everywhere. Just don't write 10 versions of your program. Write one version of your program. Just run it in different backends. Yeah, and the integration with the open source ecosystem, so especially the Hadoop ecosystem, but in the streaming space, going way beyond the Hadoop ecosystem, also new tools like Kafka and other streaming machine learning libraries or so, is going on pretty quickly. And one slide that may actually illustrate this in a very nice way is this slide. That is just the number of distinct committers on GitHub. So the project started as Stratosphere sort of early. I think this is when we moved from Mercurial to Git or so. There was some decision made at some point in time. I think this was like still university-ish. Somewhere in here must have been somewhere in here was the point when we got very excited and started thinking about giving it to Apache. I think somewhere here is the point when it entered Apache, and this isn't even the latest version of this graph. So this is where we're now after a few months later, after a year later. So it's fairly nice. Let's hope it continues like that. Then that'd be good actually. You see a slightly different stats here on GitHub because I think GitHub counts only people that are on GitHub. If not everybody is, they drop out of the statistic. Okay, so much for the past. What has happened in the past year, and given that so much has happened in 1 year in the past, we've started to think, okay, where do we want to see this in 1 year in the future? And that's a pretty challenging task because I mean, if the next year is going to do quite as much as the last year did, then it's very hard to predict where this is going. I mean, how far? So what we're showing here is a bit of an idea what the current things that we add to the system will actually give us. What is the vision of let's say a good part of the committers where to take the project and what kind of hole in the space of data analytics Flink can take. So this may look extremely simple. So I'll dig into more detail later. But if you have to break it down in one sentence, what are we trying to build, then we'd call it a use case complete framework to unify batch and stream processing. May sound a bit mundane. There's more to it than it sounds on the initial point. So Flink standing in the middle, unify batch and stream processing actually means the following. There's a lot of data. Some people call it data at rest or so. It's files, something that has been written by some application, and then there's data that's coming in basically in real time. It's very often event logs or just, I don't know, sensor data pings or so that go into the system, and these go into some compute machinery where we see actually Flink being the system that handles that. And all this data that gets in is queried in various ways it's either transformed in a very standard ETL way or in a relational way. It is used to compute graphs and to analyze graphs that are composed as a mixture of static data. Think some data that you have from your previous years, and whenever a new user makes an interaction that tells you a little bit more about the taste, or somebody new registers you, basically the graph evolves in real time. Machine learning that computes models based on historic data and evolves them online. Just streaming analysis, streaming aggregations, things that look for outliers in real time. All of this together. So, in slightly more detail, what does this mean? So Flink is a distributed system, so it of course runs on many machines. And in the heart of the system, what has always been in there, although we have not advertised that all that much, is actually a parallel streaming system, a parallel data flow system that takes data as it comes in and routes it through various computations and streams it to other operations that consume it, produce new streams out of it. That is how we have always executed actually batch programs that other people run in MapReduce with, or in Spark with, here runs an operator, it pulls some file, it does something and writes another file. Inside Flink, this has always been like data in motion, right? And in some sense, this is just, and we have done actually batch processing on top of a streaming system, which may sound like a weird thing initially. Nobody else has done it, but we're growing actually more and more happy with having decided to do exactly that. Because this is sort of now a template architecture for exactly what I've started describing on the previous slide. We want this thing to become basically the data routing, the data processing system for a data center that consumes data from historic sources, from event sources on the fly, routes it through machines, through computation, does analysis on the fly, triggers alerts, and so on. All of that with all the guarantees that you need about latency, fault tolerance, failover, and all the high-level programmability that you need for that, because nobody's going to write, a distributed, I don't know, producer-subscriber data streaming model, but people write high-level problem descriptions like an ETL transformation pipeline, a graph algorithm, a streaming data job. So one thing that this also needs, which is sort of important to point out, is actually a system that can, at the engine level, do both things. The event logs that come in real time, process them in a low latency streaming real-time fashion, and do a very reliable and heavy lifting on the historic data, which is usually which is used to analyze, let's say, larger batches in one operation than the streaming programs. And this is something, our vision for putting together the streaming and the batch analysis really in a very deep way, both in the libraries, in the engine level, in the way of handling it in the system, in the intermediate layers is what I would like to talk about a little bit today. So in some sense, it focuses on whatever is going into these parts here. We haven't talked about it all that much, so I hope there's some details also for the people who have seen quite a few of the previous presentations. Okay, we're of course not there, so quite a bit of that is vision, a bit of this is hypothesis, a bit of this is plans of code that is almost in place, and so here are some of the immediate next steps that we want to do. And one thing to look at is, before we dive into the details of what we're adding to Flink to actually do this, is a bit of the architectures that people have started drawing for streaming data analysis. And this is the following. The very basic architecture of a stream processing kind of infrastructure is the following. It has these three steps: create, collect, and process. The create step is, it's very obvious that this is important. It creates the data streams. It is basically a set of libraries or adapters to systems that produce data. It can be just a library that captures messages from sensors, something that whenever you do database transaction, kind of does something like a log play back in a database. Whenever you do transaction, you generate like a log record and ship it. It can be just logs generated by web servers. As soon as the user has an interaction, clicks on something, you get a record. All these things that, people tend to dump in files can also be used as a source for data streams. The second part is actually a very important one also, the collect part. And it may not be immediately obvious, but there needs to be sort of a place where all these streams, some form of infrastructure where all these streams come together, get buffered, get backupped if you wish, before analysis becomes feasible. So what you can think of is this is kind of the streaming equivalent of the Hadoop distributed file system of HDFS. And the technology that's sort of becoming the de facto standard for this is Apache Kafka. I'm not sure many people have worked with this. You can think of it as a very scalable message queue. I think they try to describe it differently. They say it's like a distributed log presenting itself as a message queue. It's kind of a way of reimagining the way that data processing happens by saying everything that comes in gets logged into Kafka. So Kafka is like the database log of all events happening in the company, and it's presenting itself as a message queue to be consumed by multiple services. So this is sort of the equivalent here of the HDFS. You can think of this one being the equivalent of all the adapters that take the web server logs and put them into HDFS or whatever. So the third part that is missing is the equivalent of the part that is doing the analysis of the data that is in Kafka. So what used to be MapReduce or Hive or Spark or so, the equivalent for that in the streaming space, and you can actually venture a guess where we see Flink in these three parts, right? Okay, it's already on the slide. Okay, yeah, so this being the very simple architecture, this one here is not 100% clear yet. It's right now mostly a very diverse set of libraries used by people who do stream processing. This one is becoming more and more Apache Kafka. I think this one is still open. There are a few contenders, and I think Flink is one of them. And I'm going to show you why we think it's a very good contender for this, for like a reference kind of system for this stage. This picture, a lot of you may have seen before. People have come up with this term, the lambda architecture, which is kind of a design pattern to work around some of the, in some sense, technology missing in the current state, and in some of the management infrastructure missing. So what the lambda architecture does is it sort of breaks the whole analysis space into these two different worlds, batch and streaming, and says we have the batch layer, which works on some heavy data from the past. It computes something out of that. You can think of this being your history. You compute like a summary out of it, or a recommender model or so. You put this in the serving layer, and then you have the speed layer, which sort of compensates for all the part that is happening, but that has not yet been reflected in here, because the data here is always a few hours out of date at least, often a few days, depending on how heavy this part is that is happening in the batch layer, and it gets into the serving layer. So the serving layer may be just a key value store where you dump the computation of your model, and then the speed layer may be something like Storm, like Flink streaming, like I don't know, Spark streaming, like any system that subscribes to a real-time data source. Does something very lightweight with the data, and then possibly accesses the serving layer to retrieve some state and forward it to the user. So it's kind of the separation of the low latency and the heavy lifting concerns. People have drawn this architecture. It has, some people have subscribed to that. Some people have not, and suggested a very different architecture in turn, which looks actually already quite a bit nicer and simpler. And it's not yet as famous as the lambda architecture. It's called the Kappa architecture. It's actually advocated by the guys who make Kafka. And the idea of the Kappa architecture is to say, why actually split batch and streaming? Why not just say batch is a special case of streaming? So we can do whatever a batch system can do with a streaming system, which is actually true. Think about the following. Whenever you run a MapReduce job over a file, even MapReduce reads the file as a file stream into the system, right? So it is effectively a stream data source, only that the stream is not infinite, as what people usually think of when they say streaming. They mean an infinite stream. Every batch data source is just a finite stream, a bounded stream. If you think about it like that, then you can use the streaming system to do whatever a batch system does. The streaming operators that consume the stream, that actually do block. Think about a sort, right? A sort reads the entire stream, sorts it, and then puts it out. So it's not streaming the data through. There's like a blocking part in between, but everything around it may still be streaming. And as a matter of fact, this is how Flink has always worked. So in the Kappa architecture, they advocate that you just have multiple versions of your program, and they're all streaming programs. You have a job that is producing or that is working on some data, on maybe a part of the data in the past. As soon as you have some additional data to input, you just create like a new version of the job, or it doesn't really have to be a new version of a job. It might just get some additional input data, and the batch and the streaming parts that were sort of separate here become sort of one by just using the batch and the streaming, using a streaming system for the batch job. The argument is on the execution layer below. They're all data flows anyways. Not everybody thinks of batch jobs as data flows, but you can always represent them as data flows. So that is sort of a vision that is closer already to what we want to do, but I think we've added quite a bit on top. So when you do streaming with Flink, by the way, the stream systems that they give as examples here are, I think, Storm and Samza, which are in some sense the low-level MapReduce systems of the streaming world. So they're good. They can do heavy lifting. They're hard to program at this point. I think we've started going a bit beyond this, and I said this a couple of times before, but it's worth pointing out actually that even since the Stratosphere days, Flink has been a streaming system actually that has been executing both batch jobs and now streaming jobs, where the real difference in the Flink stack is actually more the APIs right now. The runtime is sort of the same thing. The batch API is going through a slightly different code path, because what we're doing in the batch API is we're passing this to this optimizer component that you may know if you have been a long-time Flink subscriber or also been there with Stratosphere before. It's kind of like a SQL optimizer that works on the batch API and transforms the programs. Something like that is not quite as obvious for streaming. So on the API level, the way that people specify jobs, there may be some slight differences, but after actually this optimization phase or the construction of the parallel data flow, the streaming and the batch jobs go to the same runtime again. And what we've started doing is actually building high-level libraries also on top of batch and streaming and high-level domain-specific languages. For example, the table API. The example that you saw is a very batch-style program because it starts out with a CSV file and so on. But this table API actually works also on streaming, on the streaming API. It is currently limited in the sense that it does not include windowing. So everything you do on streaming without windowing is sort of, it doesn't get too fancy. But we're actually working on adding windowing, and this gives again sort of a unification from the perspective. You have tables and you have streaming tables. The streaming tables work like tables, only that they have these windows that slide over the tables for the scope in which you work. Again, please.
One question about optimization. Would it be possible to add optimization step after each iteration, since you already know that this and that is fast? Is that already done?
Okay, that is a very deep question into the batch part. Yeah, it is. Yeah.
Can you repeat the question?
Okay, what he was referring to is the Flink Can we actually postpone this, because I think it's kind of it's kind of getting in a very different direction. So let's do it after the talk is done. Okay. So if you want to do both batch and streaming in the same system, you can offer a streaming API to people who have batch programs, but there are some things that are a little more specific to batch. You can do a little more optimization, as we said, on batch. There are some things that are slightly more specific to streaming, like windowing semantics, although it is actually possible to apply windowing to batch programs as well. It becomes actually very interesting if you do that. But there's a slight diversification that this architecture, this Kappa architecture, sort of needs, in our opinion, if you go to the top, to the APIs. And this is what we've actually started to do. Make APIs that are very, very, very similar to each other, that allow you to switch from the batch and streaming world, switch between the batch and the streaming world very lightweight. And the next step is going to be to actually have this really in one proper API, so that you start out with a streaming program and you just don't really make a distinction anymore between are you reading a data set or a data stream, with the only exception that a data set is like a stream that is not infinite and basically treats everything as if it was in one window. Yeah, pulling it both together like this in the higher level APIs is, I think, a very good approach to getting them both together. There are always going to be different code paths for the optimization. So even if we have one program, what we've sort of figured out and what we believe in is that if you do if you follow the parts that really work on infinite streams and the parts that work on finite streams, you can do a lot more. You have more degrees of freedom to change the program and optimize the program on the part that works on finite streams, aka the batch part, and on the streaming part. So there may be different code paths. The fault tolerance on the batch side can be done in a cheaper way than on the streaming side, though, so there's probably some merit in doing it slightly different, even though you don't expose this to the user. So also diversifying to the bottom is something that is sort of important. There are a few things that are building blocks for a proper stream processing system. One system that can sort of do this, what I described before as this vision of you have the system running in the data center. It's consuming sources, it's analyzing them on the fly for outliers, for patterns. It's fusing it with static data and all of that. It's actually a nice incident. This guy Michael Stonebreaker, I think, just won the Turing Award a few days ago. So it's kind of a nice thing to talk about these days. This is from something he wrote a while back called The 8 Requirements of Real-Time Stream Processing. And let's just pretend they're extremely important because it comes from a Turing Award winner. Actually, they're really good points beside that. Out of those, I think we've only listed 7 here for the sake of space and because of the fuzziness of the later points. But the really important ones are actually the first 4 ones that we want to talk. That I want to go into more detail here. The other ones are sort of clear, I think, high-level languages. We said this before, integration with static sources, kind of the fusion of batch and streaming, high availability. I think people buy into that. If you have something running in your data center for a year, it has to be highly available. So on the lower levels, what is required by systems that is also not really a given in systems that do stream analysis today. And I think these 4 points are very important here. So what do they mean? Pipelining. If you want to do proper stream analysis, pipelining means keep the data always moving. Don't do something like mini batches. As the data comes, it goes on. It's always in motion. You don't accumulate it other than, let's say, buffer it for a window to do something that has like a windowed scope. The next thing is the ability to replay. This is mostly important to tolerate machine failure. So something goes down, you have to sort of pick it up somewhere at the point where you started losing things. So you always have to be able to at least replay a part of the data stream. The next thing is operator state. This is something that is sort of very crucial. It's very hard to make, and it's sort of neglected by many of these. Has been neglected by many of the initial streaming systems. For anything that is a little more complex than just looking at a single record and deciding, you know what, I'm going to filter this out, or I'm going to, I don't know, make the string lowercase instead of uppercase or so. You need a little bit of state around. Think of somebody subscribing to a stream and just saying, I want to keep a constant overview of what are the 1,000 most frequently used hashtags on Twitter or so, right? There's going to be a state, which is how many times over the last period of so long have each of these tags occurred or so. So something like that is needed, and it is something that becomes extremely tricky if you think about that. Operator state always goes together with state backup and restore, because as soon as something goes down, you have to handle the loss of the state, and if you restore the state, the state that you restore has to be sort of in sync with what you replace, so you don't get things twice into your state and all of these things. And here are a few slides on how we're going onto these things. So one thing, pipelining. Yeah, Flink has always been pipelined, and interestingly, also pipelined for shuffles, which means also in the batch API, whenever you were exchanging data, let's say between a mapper and a reducer, the mapper and the reducer were running concurrently, and the mapper was streaming data to the reducer. So this allows you to not write a lot to disk. It makes the reasoning for fault tolerance a bit more tricky, but actually, I think Ufuk took care of that. And yeah, in some sense, on the lower level, it's just a data stream. They use the same mechanism. What people that have used Flink may actually have seen are these runtime visualizations. So if you execute a program, you can look into the program later and actually see these are the individual tasks that run, and you can see that on the timeline they always have a big overlap, right? We have multiple data sources running concurrently, the chains and the filters, and the joins and the code group that they feed into. They start running at sort of the same time when some of the other operators were still running. This is because of the streaming data exchange. The sender is online, the receiver is online, they just exchange a data stream. So this is the first thing, pipelining. The next thing, replay. How do we realize replay? There are different ways to do that. The first thing that we looked at are also, I think the people that worked on the streaming API in Flink, in the very first version were mimicking the behavior of Storm, which is that you have records coming in, you keep the records, you forward them, and once the receiver has reliably received the record, it's going to send back an acknowledgement for the record. And if the acknowledgement is not received within a certain time, a record is considered to be timed out and it is sent again. So you do something like an upstream backup of everything that comes in, and you use this for resending in case you don't receive acknowledgements in time. In some sense, what Flink is doing right now is we're also acknowledging records, but we're not acknowledging as in the sense of this one is going to tell the sender back, okay, I've seen your record. We're just saying, okay, at certain points in time, we can say that we have reliably processed all records up to a certain point, and can consider them as acknowledged and discard the replay. Up to then, we have to keep data available for replay. Currently, we do this with a tight integration with Kafka, so that we use Kafka to actually replay the data and use the acknowledgements we acknowledge into Kafka rather than into our own buffered state. But we're actually working on doing this as well in the sources for data sources that are not as friendly to backing up inputs as Kafka. The next thing is operator state. So state in operators is something that to most systems that don't do mini batches sort of comes in almost naturally just to keep state. Think about you have your Java map function or so that is invoked for every element of the data stream, and you can just have a variable in the map function outside of the map method somewhere in the class that just holds your state. The more interesting thing is how do you interface with state that is too large to fit in memory, and that is something that we're currently working on. In the current prototype that is out there in Flink for streaming, the state has to be completely in main memory. It's actually exactly like that. It's sort of just some state that your functions keep around. And also windows are just implemented as a form of custom user state. So what is work in progress is actually being able to move window state out of memory to disk instead in case it grows too large, and actually offer an interface for user-defined state to be stored in memory and on disk. The considerations there have gone pretty fast. I think we have the interface almost ready. Some of the out-of-core functionality is we're still looking for some good libraries to use there, but it is very well on the way. Actually, much more interesting I find is the way you deal with state backup and checkpointing in general, and that is something where we've recently come up with a model that I think is sort of unique, at least in the world of streaming systems that we've had a chance to look at and before. And what it is, it's sort of a version of, has a very fancy name, of the Chandy-Lamport algorithm for consistent asynchronous distributed snapshots. Huh? It's fancy. Try saying this after 5 beers or so. And the algorithm sounds fancy, but what it really is as soon as data is always in motion here in in these operators. They come here from the sources, they flow along the edges. Some data may be on the buffer, some data may be in the network, in the wires. Some data is just being used to update some state here, used to update some state here. What this really is doing is it's finding a way where we say, okay, we know that all data at a certain point is either back-upped here or it's reflected in that state. And it's a way for operators that have multiple sources as dependencies to say, okay, by the time we draw a snapshot of this state, we know that it reflects a consistent set of data inside the state and outside the state. So you can think of it as a way of we're pushing barriers to the stream that sort of push the records before them, and everything that is before the barrier is defined to have to be, that it has to be inside the state before anything further, before the state can be snapshotted, and everything after the barrier is not part of the state. So at any point in time when you lose something, you can restore that previous state, and you have to replay all the data that comes after the barrier. It's a way of drawing a distributed snapshot of the state. The nice thing is the way we have implemented this is it works actually completely asynchronous. You can start triggering these checkpointing barriers from the sources. Actually, multiple of them can be in progress at the same time. So you can trigger a checkpoint. It will start checkpointing here. If a checkpoint takes a while, you can actually trigger another one that just starts while the other one is still in progress. They can overlay, and they don't interrupt the stream processing at all, right? So after the barrier, everything goes on. It gets reflected into the state, into a new version of the state. And yeah, it just happens, the whole checkpointing happens asynchronously in the background. So that is what we're actually currently spending our time on implementing. And so our take is that this is a very good solution to the problem of operator state and state backup and restore. The interesting thing is this gives you really what people call exactly once guarantees in stream processing with a very moderate or very controllable overhead. So first of all, the overhead in terms of the data stream itself are not that high because it really happens asynchronous. You don't have to stall any of the streams. If you find a way to draw like efficient shadow copies of the state, then the entire materialization of the state can also happen in the background. So you can implement this in a way, and this is what we're hoping to do in the next month, that drawing a checkpoint is actually barely visible as overhead on the system at all, because then you can actually start drawing these checkpoints very frequently, and if they don't cost too much, and you don't have to go back too far in case of a failure. Because what this model entails is, in case of a failure, you roll back to the latest checkpoint. So if you checkpoint every 5 seconds, you're going to get a possible delay of 5 seconds in case of a recovery, plus how long the checkpoint took to make. Okay, so a little bit on what we're doing above. I've mentioned it verbally before. The previous slides were more like on the runtime. What are we adding to the system to try and get this to the point that Flink is really the distributed data flow in the data center, handling the batch and the streaming, the real time. In order to make this usable, it needs some high-level interfaces, and the ones we currently have implemented so far are the data stream API with the windowing, some more as a machine learning library for streams, and the Google Dataflow runner. Currently supporting only batch, but stream functionality is upcoming, and also the table API with window definitions upcoming. The interesting thing of the table API is it is basically a relational API, only realized as a mixture of, let's say, Java Scala functions and strings. It's very easy to lift it to the level that it's only a string, in which case it becomes SQL, actually. So the difference between the table API and SQL is just that you generate the call of table.join, and then the join string attribute, you generate this from a string which says, table, join another table with a string. They're extremely close to each other. It's basically just a matter of implementing a parser for a string that generates this program. So with the table API coming up for streaming, this is like the precursor of also adding something like SQL for streaming. The thing missing there is a very intuitive way of, let's say, defining window semantics in SQL-style strings or so, which is a matter of good grammar, good taste for syntax, and so on. it probably needs a few iterations to get this right. It's not really a technical problem. It's really more like who has a good intuition what people find intuitive to use. So if you have any good input on that, we welcome to suggest. Okay. Yeah. So far, do I have some time left, actually? I think I do, yeah. This was on what do we do to realize the ability of a true streaming system in the distributed data center. One, where we say we also want to handle batch workloads with that. And in contrast to what the people of the Kappa architecture say, I mean, we've actually run batch on streaming for quite a while now and gathered some experiences. And the theory sounds nice. It is not quite as simple as just saying, you know, what you run. You just do some blocking operators in the streaming workflow. It gets you quite far. In fact, most of the batch programs that you've written so far are doing exactly that. But there's also a limit to that. And this limit comes if you want to do things like interactive queries, fine-grained recovery, and yeah, actually even iterative processing with a more finer-grained recovery that we can currently offer it. So what has been happening in the past months is that we've actually evolved Flink from a pure streaming system to a hybrid system, a hybrid runtime that is internally both capable of actually true batch. So it is doing one operator, batch data exchange, another operator after another, and the streaming data exchange running both operators concurrently, streaming the data between them. And one way to illustrate what we've done there is to look a little bit at the architectures that have been around there in the last years. So there are two classes that we've started calling operator-centric and actually intermediate data-centric. So operator-centric is, I think, what a lot of people would come up with intuitively as a first step. You have some data sources, you have some operators like map, reduce, join, some being just a special case of reduce. And this is what the first versions of systems were really about. MapReduce can be thought of as a very special case of that. Then TES as the generalization, Dryad, which was sort of the inspiration for Flink also, and previous versions of Flink. On the other hand, there's an architecture which we've called intermediate result-centric, with the basic abstraction for everything is an intermediate data set. I think a very prominent representative of that is Spark, where their intermediate data set is the RDD, and everything that happens is basically computing another RDD from a previous RDD. And the data sets sort of capture all the logic for recomputation and so on. So failure in the case of these operator-centric data flows sort of triggers a back traversal through the graph to figure out what has to be re-executed. In some way, the same happens here, but it's defined slightly differently. So every data set here is defined recursively through predecessors, and it's just triggering a recursive computation, a failover, if you wish. So what actually the newest version of Flink is doing is it's sort of mixing both models together, because quite frankly both have their advantages. The operator-centric model has a good way of representing computation, which makes it nicely debuggable, which is for streaming actually the right thing, because in streaming you want to represent distributed computation mostly. For batch and for interactive queries, the intermediate dataset centric model has some nice advantages. It especially when it comes to like more interactive queries, this is definitely valuable. So what we've tried to do is, it sounds actually sort of simple. We've sort of thrown both together. So what we do now in Flink is still similar to an operator-centric thing. So we still maintain a distributed graph of all the computation, but we've made the intermediate results a first-class citizen in there. So every time in the cluster, when an operator can always address an intermediate data set, request data from there, and so on, it makes it very easy to like interactively grow the computational graph to to implement, to also implement the recursive fault tolerance with different strategies on top of that. And what in the end, what this boils down to is really a bit of a separation of how things are handled in partly in the operators, partly in the intermediate results. And that is the following. So operators are in Flink, in the newest version, responsible for just expressing some form of computation. A map operator on a stream and on the batch, it's exactly the same. Actually, even a lot of the other operators on batch and streaming are exactly the same. Some of them do slightly different state handling, like a join on streams and a join on batches, just things slightly differently. A join on batches will probably use an asymmetric hash join. A join on streams most likely a symmetric hash join. So there are like slightly different implementations in there, but that's not a very big deal. The main differentiator between the way that the newest version of Flink handles like a proper batch thing and a proper streaming program is the way we express intermediate results. So intermediate results are in Flink a handle to data produced by an operator. And when operators are executed in the cluster, what happens? Let's say we start this operator, the join, and it registers an intermediate data set that it produces. Depending on the characteristics of this intermediate data set, the data set itself is responsible for saying, okay, I am actually a pipeline data set, so I require my consumer immediately. If it is a batch data set, then it doesn't. Then it's first completely computed before the receiver is brought up. In that sense, the data sets coordinate the handshakes between producers and consumers, and we've made them sort of parameterizable. So there are different versions of this intermediate data set that we currently support. Pipelined or batch, where pipelined means the data set is never there as a collection. It's just a handle to some data that is in flight, that is consumed by the consumer as it is produced by the producer. A batch data set is the exact opposite. It's a handle to almost like a physical file. The data sets can be ephemeral or checkpointed in the sense of they go away after they're consumed once, they stay around after they're consumed once. They can be with or without back pressure in the sense of having flow control, that a slow receiver will actually call the sender to slow down a little bit so you don't have to buffer up too much. Or you want them completely asynchronous because you don't want any skew or so to influence the distributed computation. This is the abstraction that we're working with right now, and with that, in the latest version, what's actually happening, if you're running a batch job in Flink, there's actually a fair chance that parts of the job are actually executed as a streaming job, and parts of the job are executed like a batch job. So it kind of mixes them. So it can actually be that, I mean, in this case, probably all intermediate results would be streaming intermediate results, but there are also cases when you go to more complex jobs where we're inserting batch barriers because we think it's a very good idea to separate this part of the job from the previous part of the job. So in some sense, it becomes a batching of streaming programs or so, right, that the system does internally. Okay, I know there was quite a bit to take in, so I'm happy to say that I'm done. If anybody remembers anything from what I just talked about and has questions, go and ask now or get one of the Flink committers that are here over a beer, and thank you. So the question was, what is the roadmap for the integration with Python in the short term? Because Python has nice APIs both for machine learning libraries, tools, and also for higher level APIs with something like data frames, pandas, and so on, right? So the Python API is sort of waiting to be merged. It is something like, it is the same thing as the dataset Java Scala APIs here. You can sort of use it to write functional programs in Python that get executed in parallel. It's not something like emulating Python within the JVM. The rest of Flink is in Java, but it's really calling into proper Python processes. You should be able to, like a C Python process, you should be able to use any library that is there in Python. So that should actually give you like a decent degree of freedom. Something you can also do is the Python API you can think of, you can either use it, write everything in Python, or you can write, let's say, a Java program, and you can also embed a piece of Python code in a Java program. So you can write your, let's say, the majority of your program in Java, and then let's say there's something in NumPy or so, some function that you really want to use, because who the hell wants to implement this themselves if generations of people have spent optimizing that. So you can use this to call, to embed like a call into a Python function in Java, so you can sort of mix it in there to use the Python system, the Python ecosystem also in other parts. Yeah, other than that, we don't have something like the table API integrated with Python as of now. That is, which would be something corresponding to the data frame or pandas API. That is not yet there. I mean, if we find more people getting excited around Python, there's no reason to not try and do that. It's not in there. So right now, the Python release is correspondent to Java Scala, but with Python library and Python library support. I'm not sure. Is there any interest in making use of Python machine learning libraries in the machine learning API? Something that, I don't know, we may ask some of the machine learning people or so. The machine learning library itself is definitely very much inspired by scikit-learn, which is the Python machine learning library in terms of defining learners, transformers, and pipelines. So there's a bit of Python mind share also in the other parts of the system. Yeah, you can think of it like that. Okay, there was another question, I think, no? So somebody at least raised his arm and...
I want to say support for that, so... we're
okay.
also heavily using Python. What I would be interested, are you also planning for, I think when you were at our company, Fernando asked you that, are you planning to have more like performance cluster schedulers, also support for that, like for Slurm also? So that one can run it on a scientific computing cluster? That would be really cool because not everyone is computing everything on the loop.
Yeah, so adding more backends has become almost something like a routine thing for us. So depending on what interface this offers, it's something. It's
probably it's quite cool. We used Spark account. It's quite cool, but Spark sucks after a while. So when the node gets slow when it starts caching or something like that. But actually, that would be really cool because I think you're far more better than Spark maybe. So
maybe, yeah. So the way these other backends sort of work right now is that we use them to bring up the working algorithms and the working processes defined in here. So if there's a simple way to just tell Slurm, bring up this process with that configuration there, which I think actually that's exactly what it does. There's no reason not to use it to bring up the task managers, which are these things. They're just actually processes. They're sort of fetch processes because they encapsulate multiple threads of computation plus intermediate results, network stack, and data exchange. If we can just use this scheduler to bring up these processes, yes. In theory, it's always simple. You can ask Robert. He's done this a few times by now, I think. The basic thing, just to get the processes running, is very easy. What takes usually longer is the tooling around it to make sure that also a hanging process is properly recognized by the monitoring tools and all of that. But a simple proof of concept version is probably a very simple thing to do. Just start in Flink, they're called task manager processes with a given configuration that they find the master, the coordinator process, and that should be good. All right, thanks.